Good evening, and thank you for coming to listen to me talk about neutrinos tonight. So as Jim has already mentioned, the experiment I work on is cited in Japan, where even the ice cream has Hello Kitty branding. So the first thing I'm going to start with is talking about what are neutrinos. But actually, that's not a good place to start. I'm going to start first by talking about what are fundamental particles, because neutrinos are a type of fundamental particle. So everything around us is made up of molecules, right? Including, for example, this glass of water, made up of molecules. And those molecules are in turn made up of atoms. So here I show a water molecule, an image of a water molecule, which has 2 hydrogen atoms and 1 oxygen atom. Okay? And these atoms, in turn, consist of a small dense nucleus, maybe better to use a typical atom over here, a small dense nucleus, and it's that nucleus that carries most of the mass, most of the stuff that makes an atom heavy. And then zinging around that in sort of orbits, almost like planets going around the sun, are another type of particle called electrons. Okay, now so our oxygen atom, which I've drawn here, has got in its nucleus, it's got 8 protons and 8 neutrons. And all nuclei are filled with protons and neutrons. Okay? So the protons have a positive charge, and the neutrons don't have any electric charge. They're neutral. Now the protons, in turn, you're going to start to wonder where this is going to stop, aren't you? The protons are made up of other smaller particles that we call quarks. And I've drawn them in here. Now, as far as we know, actually, that's where it stops. Atoms used to be thought to be the final thing, if you like, the innermost thing. Hence the name. The name is from Greek, actually, and it's atomos, which means not cuttable. So, for example, if you go to the hospital for an appendectomy, they're going to cut out your appendix. Okay? So that's where the word comes from, atoms. And they were thought to be uncuttable, atomos. Turns out that they're not. We now know that they're not uncuttable. They can be split up because they've got this nucleus and electrons. So an atom actually turns out to have substructure. Therefore, it's not a fundamental particle. It's made up of smaller constituents. Okay? Well, as far as we can tell, these quarks and these electrons are fundamental particles. They're not made up of something smaller. They're not composite. That's it. That's the end of the road. Okay? So now you know what a fundamental particle is. So everything in the universe is made up of a very few types of fundamental particles. So those fundamental particles form atoms, and then the atoms form molecules, and those make up everything we see around us, the water that I drink, the food I eat, you, me, the earthworms, the trees, the stars, the whole works, all made up of a very few fundamental constituents. So what is it that causes them to glom together and form all of this marvelous and vast array of different kinds of structure? Well, they're held together via these forces. They interact with each other via forces, and that's what keeps them together. So for example, if you look at an atom here, as I mentioned, the protons have a positive charge and the electrons have a negative charge. So the electrons are held there orbiting around the nucleus because the electrons are negative, the protons are positive. They attract. So they're held there because of the electromagnetic force orbiting around the nucleus. In the same way that the planets are held orbiting around the sun by a different force, the gravitational force. Okay, so you don't see anything in between them, but there's a force that permeates that empty space in between them that causes that particular behavior. The electromagnetic force is also responsible for combining the atoms into these molecules. That also happens because of the electromagnetic force. Now, it's a different force that glues the quarks here inside things like protons and neutrons, and that's called the strong force. Now, if you're a particle physicist, as I am, you'll find that there's an enormous set of rules regarding how these particles interact with each other via the fundamental forces. But we don't care about those tonight. Okay? Not concerned with those tonight. Instead, I want to go back and focus on the electrons. Turns out that the electrons have some heavier brothers. Okay? Now, this is a little bit deceptive because they're actually no bigger, they're just heavier. Okay? So each of these bigger brothers of the electron is exactly a clone of the electron, the same charge, all the same properties, interacts in all the same ways. It's just heavier. And we've given them some cool Greek names. So there's the electron that you're familiar with. I mean, this is the thing that makes electricity, right? It's these things that are the charge carriers inside any electrical circuit. So you know these, you like these, they're nice. Okay, and then their heavier brothers are the muon and the tau particle. And these are named after the Greek letters. These are the Greek letters mu and tau. And as I promised, they have the same charge, all the same properties as the electron. And in addition to these, each of these have some neutral partners called neutrinos, meaning little neutral ones. Okay? So these little neutrinos, you know, like my little bambino, only it's a little neutrino. These come in 3 types, one for each of these charged particles here. That's their partner. So there's an electron neutrino, a muon neutrino, and a tau neutrino. And again, this is the Greek letter nu. So that's where that nicely ties in with their name. Now, sometimes you'll just hear me refer to these by shorthands as nu e, nu mu, and nu tau. Okay, so we can consider these neutrinos, which are all identical to each other, except that they have different partners. We can consider these to be 3 different types or 3 different flavors of neutrinos. And I know now you're disappointed because you thought maybe we could actually taste them or something, okay? Really, it's a way just of denoting that you have different types. Also, the nomenclature is arbitrary. We could have called this the vanilla neutrino, the strawberry neutrino, and the chocolate neutrino, and that would have been fun, but I think it would have been confusing because then how would I ever know which one was the partner of which one? So typically we just refer to them as electron, muon, and tau neutrinos. Okay, so we're finally at the point where we're talking about neutrinos. Now, neutrinos are chargeless, right, neutral. They're almost massless, such a tiny, tiny mass, and they have this property we call flavor. Okay, well, you know, they're not charged, so they can't interact via the electromagnetic force. So that means that unlike an electron, for example, they're not going to be confined inside an atom going around a nucleus. Why? Because they don't feel the electric charge that's coming from the nucleus. It's nothing to them. They don't see it because they're neutral. Okay? And they don't have the property that would be required for them to interact via that strong force. Remember, that's the force that keeps the quarks bound up inside protons and neutrons, which are then inside the nucleus, inside the atom. They don't have a property that they would need in order to interact via the strong force, so they don't do that. That's a property we call color. Well, that only leaves one force they can interact with, and that's via the weak force. And I'm going to come back to the weak force in a minute. So they're not bound inside atoms, and they're not bound inside the nucleus, and yet the room is absolutely full of them. They're all over the place. They really are. The place is full of them, and you don't even notice. So where do we get them all? Well, it turns out that many nuclear processes, like the thermonuclear processes that power the sun, produce bucket loads of neutrinos. So there are loads of them coming to the Earth from the sun all the time, just because of the sun burning, nuclear burning. That produces loads of neutrinos. Also, cosmic rays, which are particles, tiny particles that are produced by stars anywhere, extragalactic ones inside our galaxy, our own sun. These cosmic rays come when they hit the upper atmosphere, the Earth's upper atmosphere. That's denser atmosphere than where they've been, and so they start interacting in that atmosphere, and when they interact, that produces neutrinos, and those come to the Earth as well. And then very conveniently, nuclear reactors, of course there's nuclear processes happening in them, so those produce a whole bunch of neutrinos too. So that's a good place to see some. And then sometimes we want a specific type of neutrino, and so we'll make them ourselves in a dedicated particle accelerator. But let's come back for a minute to that weak force. Okay, so what is it about the weak force? How weak is it? Well, actually, the weak force is not weak. We just call it that. It's not weak, but what it is it's extremely short range. So unlike the electromagnetic force, if you remember my model of an atom, you know, you've got this small, dense nucleus, and then you've got electrons out there. The entire space, as I said, between the protons, they produce an electromagnetic field because they're charged, and the electrons, that entire space is full of the electromagnetic force because the electromagnetic force has an infinite range. It gets weaker and weaker the further away you go, but it goes on forever. Well, the weak force is not like that. It's extremely short range. So if we consider here, again, let's pretend that this is a model of the atom. This, I believe, is the football stadium of Real Madrid. Does anyone know for sure? Is it? Do you think so? He doesn't know. He's nodding. So I think we're right. Okay, so it's a football stadium of Real Madrid. Now, pretend that there's a P in the middle of it. There it is. There, well, honest. There's a P in the middle of the football stadium. Okay? And let's pretend that in our model, that P represents a nucleus of an atom. In that case, the electrons are somewhere way out past the furthest reaches of the seats. Way out here somewhere is where your nearest electron orbital is. Way out there. In between there is just vacuum, except the vacuum isn't actually an empty place because it's permeated by that electromagnetic field. Okay? But apart from that, you know, it's just vacuum. There's nothing there. Well, so what does that look like to a neutrino, bearing in mind that the neutrino does not see electromagnetic fields? Well, sort of like that, really. Except I think that the P in the middle would actually probably look a lot smaller to a neutrino. So a neutrino needs to hit a nucleus or an electron like this dead on before it's going to interact. So what are the chances? Not very much, actually. For example, a measure of what the chances are is shown here. The neutrino interaction cross-section, okay, sort of complicated words, but it's actually a measure of how big a target looks to an incoming neutrino. So how big does that P look there to an incoming neutrino? And the answer is about 10 to the minus 43 square centimeters. What is that? That's 1 over 10, let's see, billion, trillion, 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 trillionth of a centimeter squared. Okay? So it looks pretty small. So what are the chances the neutrino is going to hit that? Well, let's see. How far would a neutrino travel on average before it runs into anything? Well, in lead, it would travel about 10 to the 17 meters. In water, about 10 to the, in lead, about 10 to the 16 meters. In water, a little bit more, but still 10 to the 17 meters, about a light year. It's going to go about a light year before it actually runs into something and interacts. So that's not very likely that it would happen. So if we compare that with an astronomical unit, the distance between the sun and the Earth, which is, 100 million kilometers, okay? Now imagine, but you say, yeah, of course it's going to get from the sun to the Earth. There's almost nothing in its way. What's it going to interact with? Okay, fair enough. Well, let's pretend that we fill up the distance between the Earth and the sun with lead. Are you visualizing that? We are filling up the distance between the Earth and the sun. Oh, here, let me help. There, that's better. Okay. So we filled up the distance between the Earth and the sun with lead. That'll stop the little beggars. Well, actually, no, it won't. 99.999% of the neutrinos won't even notice you did that. They'll just get right on through. They won't even notice. Right through all that distance of lead. Wow, okay. Well, what if we get really serious about it? Alpha Proxima is our nearest star. Let's fill up the distance between us and Alpha Proxima, which is 4 light years away, with lead. Now, that's got to work a little bit better because I know that the mean free path of a neutrino in lead is about a light year. And this is 4 light years. So for heaven's sake, seriously, if you do that, yes, you will stop most of the neutrinos, but about 2% of them will still go through. You filled up the distance between us and our nearest star with lead, and some of them will actually still get through. So they're pretty incredible little critters. So for that reason, neutrinos are often referred to as the ghosts of matter. If you look, for example, at your thumbnail, okay, at your thumbnail, see your thumbnail? 1 billion neutrinos just went through there. Every second, billions of neutrinos go through every square centimeter of you. Amazing, right? Billions of them. And you don't feel a thing. So what does that tell you? It tells you that you are not a very good neutrino detector. Okay, so we're not going to use you to detect neutrinos because, boy, that sucks. Okay, but we haven't got to the good part yet. Okay, the good part is that neutrinos change flavor. So they actually change from one type to the other. Okay, so this is a little bit of a heavy slide, but stay with me because I think I can make this work. Okay. So consider my electron neutrino and my muon neutrino. So we can think about neutrinos in terms of their flavor, electron and muon. Let's just pretend there's 2 for a minute. Forget about tau neutrinos. Oh, you already did. Okay, so let's just pretend there's 2, electron and muon neutrinos. We can think about that in terms of their flavor, or we could think about them in terms of their mass. We have a lighter mass state called nu1 and a heavier mass state called nu2. Well, that was creative naming. Anyway, now that's okay, right? Because you could do that with ice cream as well if you wanted to, right? You could say, here's vanilla ice cream and here's strawberry ice cream. I've got vanilla and I've got strawberry. But that's not the only property that my ice cream possesses, okay? I've also got hard ice cream and soft ice cream. Okay? So I can think of it in terms of whether it's hard or soft, or whether it's vanilla or strawberry. Now, pretend that your vanilla ice cream is made up of some hard ice cream and some soft ice cream. But also, someone has really been in the buckets and mixed it all up, because also some of your hard ice cream is made up of vanilla and some of strawberry. And some of your soft ice cream is made up of some vanilla and some strawberry. Now, when you dip into your bucket, you're going to find that, because it got all mixed up, your vanilla ice cream, which had some of the soft ice cream and some of the hard ice cream, well, because those were mixed up, now you've got some vanilla and some strawberry in there. Is that okay? Yeah? All right. Okay. So let's take it back to neutrinos, because neutrinos are like that, but there's a way they're different, and I'm going to come to that. So nu-E is made up of a mass state, nu1 and nu2, where nu1 is the lighter one, nu2 is the heavy one. Nu-mu is made up of nu1 and nu2. Okay? But this light mass state, nu1, is made up of nu-E and nu-mu, and the heavy mass state is nu-E and nu-mu. So when I put it all together, that means that nu-E contains both nu1 and nu2, but therefore it contains some nu-E and some nu-mu. And it's the same story with nu-mu. Now the thing is, okay, that when we produce an electron neutrino in the sun, for example, via thermonuclear processes, it's pure nu-E. Well, how can that be? It's got nu-mu in it. It's right there. What's the matter with you? But it's not ice cream. It's actually neutrinos. And we describe how they behave using mathematics. Now, look at how much nu mu is in each of these mass states. It's the same amount. What happens when the nu E is produced is that this one comes in out of phase with this one. Mathematically, that means this one has a negative sign and that one doesn't, so they cancel out. It's like magic, isn't it? So when the nu E is produced, it's all nu E, and you can't do that with your ice cream. Okay? And it's the same story with the nu mu. When it's produced, the nu E comes in with opposite signs, opposite phases, and so they cancel out. And so when it's produced, the nu mu is just nu mu. Oh, but now, one last thing. Now the little suckers are going to go on a trip, and they're going to travel. Okay, fine. So I produce my nu E in at a particular energy. Now they're going to travel. But hang on, this one's heavier than that one. So if they both have the same energy, this one has to go slower than this one. Well, you know what? If this one goes slower than that one, now all bets about that phase difference that was canceling out the nu mu, all bets are off. Okay? Once it travels, that can change. So when I detect what was my electron neutrino a little bit later, possibly the nu mu part is not canceling out. And you can't do that with ice cream either. Okay, and to help you to remember this and keep it all a little bit, in your memories, I've made up a little nursery rhyme. How many people here have ever heard any Dr. Seuss? Read any Dr. Seuss? More common in Canada and the States, but lots of people have. Oh, good. Like, what is it? 1 foot, 2 foot, red foot, blue foot. Okay, here's my nursery rhyme. You ready for this? Nu E and nu mu are nu 1 and nu 2. Nu 1 and nu 2 are nu E and nu mu. So nu E is nu E, but it's also nu mu. And nu mu is nu mu, but it is nu E too. Thank you, I wrote it myself. And they lived happily ever after. But we're not finished, to be continued. Okay, so if your brain is feeling a little bit like this right now, okay, this is your brain, yeah, then don't worry, because we're going to have a little experience too probably. So bring on the ice cream, and here the ice cream comes. Okay, but there are rules. Don't just dive into the ice cream. Okay, you'll notice it's Neapolitan ice cream, so it has 3 flavors. Yeah? Okay. Now, this is too much fun. So what I want you to do with the ice cream, okay, you guys ready? Don't taste it yet. Okay? What I want you to do is, we're going to do a little experiment, and I don't want it biased by your personal preference for strawberry or something, okay? So, no eating it yet. So what I need you to do, no, don't put any on your spoon yet. So what I need you to do is, without looking at it, okay, I want you to sort of like keep your eyes closed, and without messing it up, I want you to turn it around somehow till you don't know what flavor you'll get, okay? And then I want you to dip your spoon in and take a mouthful, and by taste, identify what flavor you've got. And after that, you can open your eyes. Okay? Oh, they don't have spoons yet. Ah. Oh, I think Andrew has spoons here. Oh, wait, I'm going to ask. Remember, hold that thought. I'm going to steal a bunch of spoons for the people down here. Whoops. Can I get you to hand those along? Yeah, sure. They're spoons. And yeah. Oops, sorry. So once you have a spoon, okay, we're going to do our experiment, okay? So we've got our ice cream, okay, but it needs to be vanilla. I mean, it needs to be Neapolitan, okay? So we've got our Neapolitan ice cream, okay? And I thought to avoid embarrassing anyone else, I'd use pictures of me. Okay. Now, remember what it is. Yeah, you got it. That's it. Yeah, don't cheat. Don't cheat, because I want to take, a little bit of a statistical average. So I think people still have yet to taste their ice cream. So remember, you want to turn it till you don't know what flavor you'll get. Then dip in and remember what flavor you got, okay? Okay. Now, then, How many got chocolate? Quick count. 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10. I've got 10, 10, 10, 11, 11, maybe 12, 12, 13, 14. I don't know, maybe 13 or 14. You remembering this? Yeah. Okay, okay. So how many got strawberry, Hello Kitty? Oh, see, I told you people prefer strawberry. I bet you cheated. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. This is not very scientific. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, maybe 25-ish. Okay, okay. And you, also maybe 26-ish. And how many got vanilla? Oh, wow. 1, 2, 3, 4, 5, 6-ish. Okay, okay, something like 6 or 7. Okay, now, if those were actually neutrinos, the minute you tasted, say, strawberry, then the whole thing would have been strawberry. Honest. It's a quantum mechanical thing. The minute you make a measurement, the minute you taste it, the minute you detect it, the minute you thought, that's strawberry, your entire dish would have been strawberry ice cream. Seems a bit of a cheat, doesn't it? Okay? So that's how neutrinos are not like ice cream. But there are lots of ways in which they are like ice cream that we've been going through, but that's one of the ways that they're not like ice cream. As soon as you detect a neutrino and you say, well, that was a muon neutrino, that's it, then it was a muon neutrino. In physics speak, you collapse the wave function into that state. Okay? This will work for the physicist. So what do we want to know? Neutrinos change flavor. They're produced in a particular flavor. As they travel, somehow flavors get mixed up, and when you detect them at some later time in a different place, their flavor might be the same, or it might not be the same, it might be different. When you detect them as a flavor, they are entirely that flavor. The other thing that would be different with your ice cream is that you would have never seen 3 flavors in the first place. They would have been produced in a pure flavor state. Okay? And then somehow magically been able to change flavors so that when you tasted them, they were some other flavor state. Okay? Now we can predict this. Okay, think about your ice creams. If you wanted to predict which flavor you were going to get, what would you want to know first? Okay, well, if it was me, I'd want to know the admixture I was beginning with. What percentage of that ice cream was vanilla, what percentage strawberry, and what percentage chocolate when it started out? I'd want to know that admixture. The other thing I'd want to know is, okay, let's pretend that it's getting to me, and the way that it's going to change flavor is by spinning as it comes towards me. Then I'd want to know how fast it's spinning and how long it's traveling. Now, if I knew those things, I could probably do a pretty good job of predicting, and if I knew what flavor it started in, then I could probably do a not unreasonable job of predicting what flavor I'd taste when it got to me, right? Well, guess what? We have this mathematical formula that I've put here. This Greek letter theta, that's called a mixing angle, and it tells me the admixture of neutrino flavors that are in my neutrino when it starts. Yeah? This delta m squared, that's the mass difference between the nu1 and nu2, between those mass states, and that drives how fast they're going to change flavor. So that drives, in my analogy with the ice cream, how fast your ice cream is spinning. Okay? And this L, that's the distance the neutrino travels. And then this E is the energy of the neutrino. That's also going to drive how fast it changes flavor. So I know those things. Well, good, then you say. So what, Laura? So can you predict it? Well, check this out. All right. Is that impressive or what? This is, okay, I didn't actually do this. This is from the Camland experiment. This is from the Camland experiment in Japan. Camland is an experiment in Japan that uses neutrinos that it detects that come from 55 nuclear reactors sited around Japan. Japan has a lot of nuclear energy. That's why Fukushima was a really big deal for it. So here we are. These, And these nuclear reactors are different distances from the CAMLAN detector. Okay? Now, these points are the data that they've measured, and they're doing an experiment not unlike the one you just did. They're starting out, they know that all their neutrinos are actually produced as electron neutrinos. Okay, well, actually it's anti-electron neutrinos, but never mind that for the minute. It doesn't really matter. So they start out with a bunch of electron neutrinos. Now what they plot with these data points is how many anti-electron neutrinos they see if they check at different distances and energies. Okay, that's what that is here. So they're checking at different distances and energies. Now, they're saying, how many do we get out of how many we know were actually produced and headed our direction? So if all of the neutrinos that they detected, all were still electron neutrinos when they got to CAMLAN, okay, then all the data points, all those black data points would lie along this line at 1. That's equivalent to 100%. And none of them lie along there because there is no position, no combination of distance and neutrino energy for which all of them are still electron neutrinos when CAMLAN sees them. Instead, what you see is that sometimes 80 or 90% of them are electron neutrinos. Other times, only 20 or 30% of them are electron neutrinos. And the rest are other flavors of neutrinos. Is that okay? Does that make sense? And you can see that this is, if those of you who are familiar with a little bit of math, you can see that, as one would expect, it follows a sinusoidal waveform. Okay? So this is actually a probability wave. Okay? So in neutrino physics, we make waves. We make probability waves. So this is the probability that neutrinos that were produced as anti-electron neutrinos, it's a probability that they're still going to be anti-electron neutrinos when we detect them at some distance further away. Okay? Now you say, how do we know that that is modeled well? Well, the blue line, the points are the actual measurements, the data. The blue line is the prediction we get. It's the curve we get actually if we use this equation. And I would say it does pretty well. So how do we detect neutrinos? I've told you over and over again that they never interact with anything. You know, in order to find out the properties of any particle, we really need the particle to do something. It has to interact. It has to do something, or we can't measure any of its properties. We couldn't have made that CAMLAN plot if the neutrinos didn't interact in the detector. So what do? Well, we use simply enormous detectors and loads of neutrinos. That's why CAMLAN was in such a good position, sort of hanging out in the middle of 55 nuclear reactors, right? So here is the detector, Super Kamiokande, that my experiment uses as what we call its far detector. Super Kamiokande is a cylindrical tank that is 40 meters wide by 40 meters high, filled with ultra-pure water. And these little bubbles that you see around here, those are photomultiplier tubes. And a photomultiplier tube takes any light that's incident upon it and converts it into an electrical signal. Once you have an electrical signal, then you're happy because now you can manipulate it with electronics. It goes into computers and you can do data analysis with it. Okay? These here, that's 3 Japanese men on a boat when the detector wasn't yet filled with water, attending to some of these photomultiplier tubes. So that gives you some idea of the scale of that detector. It's just enormous. Now, it's true that neutrinos don't interact electromagnetically, but they do interact weakly. So if we have enough of them, and if we put a big enough target in front of them, some of them will interact. And often when they interact, they produce their charged partner. So an electron neutrino will produce an electron. A muon neutrino will produce a muon. Now, those charged particles in Super Kamiokande, in that ultra-pure water, these charged particles can be given enough energy that the charged particle that's produced when, say, a muon neutrino interacts goes faster in the water than light can travel in the water. That's okay, that doesn't break any rules. Nothing can travel faster than light in a vacuum, but an ultra-relativistic particle can travel faster than light in water. And it will. And if it does that, then you get the same sort of effect that you get when a supersonic jet breaks, goes faster than the speed of sound, breaks that sound barrier, and you get this big boom. Well, you get that in this detector, only it's done with light, not sound. So what you get is when a charged particle goes through water faster than light, you get a big cone of light that spreads out from along the particle's trajectory. Okay? That cone of light, that's what we've got all these photomultiplier tubes for. It's picked up by the photomultiplier tubes. So a muon neutrino that interacts and produces a muon, okay, that muon will then leave a signal like this in Super Kamiokande, where the central part is the cylindrical part of the detector folded out so that you can see what's happened. And then this and this are the top and bottom caps of the detector. Okay? So a muon neutrino will create a muon that produces a ring like this of light in the detector. An electron neutrino will produce a fuzzier ring. So not only can we tell you they're there, but we can tell you which type of neutrino it was. That's sort of fun, hey? So that's the big detector. Now I'm going to come to the point of making loads of neutrinos. So the experiment I work on is called T to K. It stands for Tokai to Kamioka. We produce a beam of muon neutrinos here on the east coast of Japan, near a village called Tokai. And we aim those neutrinos sort of under the Earth because it's 295 kilometers away. So you sort of have to go underneath the curvature of the Earth to get there. We aim those into the Earth at the Kamioka, to Super Kamiokande, which is underneath the mountains, in the Kamioka Mountains. And then we want to look to see, out of all the muon neutrinos we made, how many are still nu mu, and how many have changed to nu e. Okay? So that's the point. Because that will help us to measure that mixing angle. That's going to tell us what the admixture is of nu e, nu mu, and nu tau when our neutrinos are produced. Okay. And this is a picture of the J-Park facility in Tokai, Japan Proton Accelerator Research Complex or something. And you can see here it's right by the Pacific Ocean, actually. This is an actual aerial view of the thing. Right by the Pacific Ocean along the east coast north of Tokyo. Does that ring any bells? Yeah. So that actually is the area that was hit by the earthquake and the tsunami about 1.5 years ago. Happily, we just seem to be in a little bit of a tsunami shadow, and it pretty much missed us. Thank goodness. The earthquake, we did have a bit of tidying up to do after that. There were some components that needed replacing and stuff. But overall, the experiment's back up and running now and taking good data, so we're happy about that. So to produce neutrinos, we actually start off by making protons. And we start off with them in a linear accelerator, and they're sped up a little bit, and then they go into a synchrotron, and they're sped up more, and they come into this main ring. Then we get a great big magnetic pulse to kick them off into the neutrino beamline, where they go first through some near detectors. Think about it. If we want to know how many neutrinos that were produced as muon neutrinos here end up changing into, say, electron neutrinos here, then what we need to know first, and very well, is how many muon neutrinos we started off with. And that's the job of these near detectors. These ones that are right here, right near where the neutrinos are produced, we need to characterize the muon neutrino beam very well before the little beggars have a chance to change flavor. Okay? We need to know what we've got to start off with. And then the beam carries on and goes on 295 kilometers to Super Kamiokande. Okay. So what do we start with? Well, we actually start with 800,000 billion protons, all in that many seconds, every 3 seconds. So that is actually more protons than are produced by the LHC beam. Actually, if you've heard of the one at CERN, the big beam where they found the Higgs, bloody blah. Harold will tell you about that next week. We actually produce more protons than they do. They produce higher energy ones, but for intensity, we produce more. So those protons smack into a target. It produces particles. Those particles then produce muon neutrinos. And then the big trick is to just send those muon neutrinos through a lot of stuff. So we send them through a bunch of iron, and then we send them through 250 meters of rock. And at the end of all that, guess what? Nothing's left but the neutrinos. Okay, so any other particles that were made in that beam, those are gone by the time you send it through all that crap. Okay, and then it goes into the near detectors where we can characterize the muon neutrino beam, and then it carries on to Super Kamiokande far away. One of the things that we did at Lancaster was to make part of the near detector. That's the part we made down here. It's bigger than it looks. That was made, that's looking from above. So that is a part of the detector that we built. Here we are building that part of the detector. This is one of the layers that go into that detector. It's made of scintillator bars and lead. And look, I have what we call the baby prototype, right? Which I can hand around. Here we go. So that's, yeah, see, everyone always does, see, lead is actually really heavy. The lead in that is only 1.75 millimeters thick. It's really thin. It's just a thin sheet of lead. But lead is really dense stuff, right? You don't realize it. Oh, and that's all painted over so you won't get lead poisoning and stuff. So, you know, not that I advise licking it. Don't lick it. But you know, it's still all right. So that's, and what you see in there, oh, yeah. Actually, these, you know what, you can keep a piece of those each, actually. I've got, that's bits of scintillator, actually. That's that scintillator bar. So the deal is a charged particle going through here will actually light up this plastic scintillator. And that's how we can tell what happens. So you see, this is a neutrino interacting in that near detector. The bit that we built is this bit down here, okay? You can see it just lighting up there. And in 3 dimensions, it looks like this. That little prototype layer I'm handing around, you can see the layers of scintillator bars lighting up. This is that type of detector right there. And the layers are put with bars going this way and bars going that way, then this way, then that way, then this way, then that way. So that where you get the confluence of those 2 planes of bars going through, like here, that's the path of your charged particle going through the detector. So what happens here? So look, this which you do not see is the neutrino, right? You don't see that. But then suddenly, seemingly out of nowhere, you get a bunch of charged particles coming out. That's because that's where the neutrino interacted. So you see nothing, 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 nothing. There's the neutrino. And suddenly you see a spray of particles going out. If it wasn't for the neutrino, this stuff would clearly violate conservation of momentum, right? You know, you have nothing, 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 and then suddenly a bunch of stuff going that way. Okay, can't happen. This which you do not see is the neutrino. And then these charged particles lighting up, those are the particles that were produced when the neutrino interacted. Okay? And in that scintillator like that. Okay, and just a few more again. So this is a cosmic ray muon going through the detector. We don't care about it. That's not the interesting bit. The interesting bit is this, what you do not say, this neutrino coming in, it interacts here in this part of the detector and produces a whole bunch of particles coming out. Now, my favorite events to look at are ones like this, because you get this gorgeous spray of particles, right? Nothing, 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 that's the neutrino. Bash, interacting, and a whole bunch of particles come out. I love that to look at, but in terms of particle physics, that's next to useless. The reason it's next to useless is because we need to be able to determine the energy of the neutrino that came in. How do we do that? Well, we sum up how much energy is deposited by all of the particles it produces, and then we say that must have been the energy of the neutrino. Yeah, but when it's got a whole bunch of stuff like this, we're bound to miss some energy. And then when we reconstruct the neutrino energy, it's actually going to be wrong. It'll be too small because we'll have missed some of the energy. Does that make sense? For real physics, the ones we like are these ones, because we won't miss that. We can reconstruct that energy, and we'll get the neutrino energy right. Sort of makes sense? Kind of? Okay, so T to K, what have we found out so far? Well, okay, look, it was T to K that first found that neutrinos can change between all 3 flavors. We found that out last year. Until just before the earthquake, actually, we got that data. Until then, we actually weren't sure that every possible change between the 3 neutrino flavors was possible. We didn't know that. And that's important. Because of that, if they couldn't do that, then the rest of this would be off, okay? But because all 3 flavors can change, it means that neutrinos might be the reason that the universe and you and I exist, okay? How can that be? Well, look, The universe is made up of matter, not antimatter. Okay, you familiar with that idea? You know, it's made up of matter, not antimatter. Well, how did that happen? That's weird, because we know from our particle physics experiments that if we have an interaction, for example, that produces an electron, then it probably also produces an anti-electron or a positron, right? Same particle but opposite charge. And that happens every time. Every time we produce a particle, we get an antiparticle. So if that happened in the early universe, and if matter and antimatter annihilate, what the heck are we doing here? Okay, really, we should have produced as much matter as antimatter. It would have all annihilated, gone kablooey. There'd be just nothing in the universe but a bunch of light, not us. So how did that happen? We actually don't know the answer to that question. It's a bit embarrassing, you know, because we know all this intricate stuff about neutrinos, but we don't know why we know that, like how we're here to even ask the questions. Well, it turns out that's possibly caused by the behavior of neutrinos when the universe was first forming, okay? And it can only happen if they change between all three possible flavors. And now we know they do. So we might be the reason that we're here at all. But we don't know, and we'd like to find out. So that's one of the areas of ongoing study. Other things we don't know about neutrinos are they their own antiparticles? You know, unlike the electron, whose antiparticle is a positron, a positively charged electron, okay? Well, a neutrino is neutral, so it can't have an oppositely charged neutrino. So what does it mean then to say it's an anti-neutrino? Maybe it's the same thing as a neutrino, okay? And we don't know that, actually. What are their masses? I told you that they have mass, and I told you that we can make some measurements of their mass difference by looking at the way that they change flavors. Remember, I told you it's the difference in masses that makes them change flavor? So we know they have masses. And we can tell you that there are three different masses, but we don't actually know what the masses are. Only that they exist, and they're not the same. And we know the squares of the differences of the squares, in fact. So we know some of the differences between them. And that's it. And it's really hard to measure because they are such tiny, tiny masses. We don't know. You know, I've told you about electron, muon, and tau neutrinos, but maybe there's more than three. There could be more than three. It's a bit hard to tell. For a long time, we thought we knew the answer to the question, and the answer to this question, and that the answer was, there's three. And now some data has come in, and we're not as sure as we used to be, actually. Now, is there an underlying significance to these mixing values when we measure the admixture of the different types of neutrinos that are produced in different situations? Is there some underlying significance to that? Because sometimes it looks to us like, given the numbers, there might be. But we actually need to measure it better before we can answer that question. And I don't know, did any of you hear that neutrinos might travel faster than the speed of light in a vacuum? That was about a year ago. You heard that bit? Yeah, so it turns out that the experiment that made that measurement, the OPERA experiment, they went back and they did a very careful further checks of their equipment, and they found some very subtle little glitches in their equipment that would have accounted for it looking like neutrinos travel faster than light. However, we're still not entirely convinced, so experiments like T to K and other experiments as well are actually checking it. We've upgraded our GPS systems and everything, and we're actually just double checking it. I would say probably they don't travel faster than the speed of light. But you know, it'd be good to check. And because they interact so seldom, if anything in the universe could get away with traveling faster than the speed of light and not have us notice yet, it would be neutrinos. Okay? It'd be them. And what uses might I see for neutrinos, apart from the really obvious one of that as human beings, we are intrinsically interested in the universe around us and how it works. So apart from just understanding the universe, what else might we do with these? Well, actually, some work is being done with geoneutrinos. These are neutrinos that are produced via the radioactive decays of things like uranium and thorium inside the Earth in the mantle. And by measuring the number of neutrinos that you get, you might get some information back on the amounts of uranium and thorium and fissionable material that's in the mantle. That can give you information about how the mantle is cooling, and that can even give you information about things like volcanoes or earthquakes. So there might be something really useful coming out of that, and that's really in early days yet. Now, carrying on with the same theme of telling how much fissionable material you have, some people are doing tests to use neutrinos as security. If you stick a neutrino detector outside a nuclear reactor, of course, as you saw from the CAMLAN data, you can tell how many neutrinos it's producing. But you can turn that around and you can say, given that you are showing this many neutrinos, we know how much fissionable material you have in your nuclear reactor. So let's pretend there was a country that you don't really trust, okay? And they were making a nuclear reactor, and they were making enriched uranium, and they say, it's all for the nuclear reactor, really. And then you can say, okay, fine, we'll just stick a neutrino detector here. You won't mind, a few kilometers from your nuclear reactor. And we're going to monitor how much fissionable material you have in it. And if suddenly the amount of fissionable material drops by half, then you can say, where did all your fissionable material go? So there are various ideas about using it actually for security. So there's still a lot that we need to learn about neutrinos, and it's not easy, but it's fun. And who knows where it might lead us? We don't know, but we know it's going to be interesting. And that's the end. So thank you very much for your attention.